Hello, today we are going to learn about tree recursion and explore how to solve problems using this approach. Let's first understand what a tree recursion is. Tree recursion occurs when a function makes multiple recursive calls, creating a branching or tree-like structure of function invocations. Imagine a scenario where a function needs to call itself not just once, but twice or more times within its own body. This creates multiple paths of execution, each potentially leading to more recursive calls. Tree recursion is especially useful in problems where the solution involves multiple smaller independent subproblems. By breaking the problem into these manageable pieces, we can solve it step by step and then combine the results. There are certain key characteristics of a tree recursion. First, tree recursion involves multiple recursive calls from each function. Instead of a function calling itself once, it calls itself several times within the same call stack. Second, this process leads to exponential growth in the number of operations. This exponential growth is one reason tree recursion can be computationally expensive. Finally, tree recursion typically involves breaking down the problem into smaller subproblems. The beauty of tree recursion lies in solving each of these subproblems individually and then combining the results to form the solution to the larger problem. Let's explore two examples that beautifully illustrate tree recursion, the Fibonacci sequence and the power set generation. Let's first understand what a Fibonacci sequence is. The Fibonacci sequence is a series where each number is the sum of two preceding ones starting with 0 and 1. As shown here, the first two Fibonacci numbers are 0 and 1. The third Fibonacci number is the sum of the first two. The fourth is the sum of the second and third, and so on. So each Fibonacci number relies on the two before it, making this problem a natural fit for tree recursion. We break it down into smaller subproblems and combine them to get the final result. The formula for Fibonacci is f of n is equal to f of n minus 2 plus f of n minus 1. Here n refers to the index or position in the sequence. For example, when n is equal to 3, we calculate the third Fibonacci number f of 3, which is equal to f of 1 plus f of 2 and is equal to 2. To define recursion, let's first identify the base cases, the conditions that stop the recursion from continuing indefinitely. For Fibonacci, we typically define two base cases, f of 0 is equal to 0, f of 1 is equal to 1. Next, we have the recursive case. The Fibonacci function is defined recursively as f of n is equal to f of n minus 1 plus f of n minus 2. This means that to calculate the Fibonacci number for n, we need the Fibonacci numbers for the two preceding values n minus 1 and n minus 2. This relationship creates a tree of recursive calls that allows us to break down the problem into smaller parts. In the lower right corner, we have the function to calculate the Fibonacci number. In this function, we check if n is 0 or 1 to return the base case values. For any other value of n, we call the function recursively to compute the sum of the two previous Fibonacci numbers. Let's take a simple case of Fibonacci of 4 and see the step-by-step calculation. The function Fibonacci of 4 calls Fibonacci of 3 and Fibonacci of 2. Then Fibonacci of 3 calls Fibonacci of 2 and Fibonacci of 1. Then Fibonacci of 2 calls Fibonacci of 1 and Fibonacci of 0. Finally, Fibonacci of 1 and Fibonacci of 0 hit the base cases and returns 1 and 0 respectively. Here is a visual of how the recursive tree expands as each call branches out. As you can see, the function makes multiple recursive calls at each step, branching out like a tree. Each branch eventually reaches the base case and unwinds the recursion to produce the final result 3. One of the main drawbacks of tree recursion is redundant computations. As you can see, Fibonacci of 2 is calculated multiple times. The biggest challenge with tree recursion is that it can be inefficient. For the Fibonacci sequence, the number of recursive calls grows exponentially. Specifically, the time complexity of the Fibonacci function without optimization is big O of 2 to the power n. which means it can get very slow for larger values of n. However, there are optimization techniques like memoization which can help improve the time complexity. Let's switch to PyCharm. Here we have the same Fibonacci function that was shown earlier. We now run the Fibonacci function with n equal to 4. As expected, we get 3. Now watch how the runtime increases as we run it with larger values of n. Here we have a function that takes a maximum value of n. It runs a loop to compute the Fibonacci number for each value from 1 up to n and displays the time it takes to compute it. Let's run this with a maximum value of 40 and observe the results. As expected, for larger values of n, the time taken increases exponentially. For example, n equal to 40 takes noticeably more time than the smaller values. Clearly, for larger values of n, we'll need optimization techniques such as memoization to improve the efficiency of Fibonacci calculation. Now that we have understood tree recursion with Fibonacci, let's move on to another powerful example, generating the power set. Let's begin by understanding what a power set is. The power set of a set is simply the subset of all possible subsets of that set. This includes the empty set, which contains no elements, and the set itself. For example, if we have a set S is equal to 1 and 2, the power set would include the empty set, each individual element 1 and 2, and the set containing both elements 1, 2. We'll soon see how we can generate this using a systematic recursive approach. To solve the power set problem using recursion, we'll start by first applying simple cases. In case 1, we have an empty set. For this set, the only subset is the empty set itself. So the power set of an empty set is just the empty set. For a set with one element, say S is equal to A, the power set includes the empty set and the set itself. This step reveals the important observation that the power set always includes the empty set and the set itself. Now let's generalize our approach from small sets to larger ones. Here we have two elements, S is equal to A and B. The power set of A and B, as we can see here, is an empty set, elements A and B and the subset AB. How can we construct subsets for A, B if we already know the power set for A? We know that the power set of A has two subsets, the empty set and the element A. For each of these subsets, we can either include or exclude the new element B. So the power set for A and B can be broken down as subsets without B, which are simply the empty set and the element A, and the subsets with B added to those, which are B and the subset AB. Finally, we combine both the subsets without B and subsets with B. This gives us the power set of AB, which you can see here as an empty set A, B and AB. This simple exclude and include method is key to understanding how we can scale the process for larger sets. Based on the observations, we can see the pattern that can help us to solve this problem. So for any set, we can generate its power set by first generating the power set of the set minus one element and then adding that element to each of the subsets generated so far. Now we are ready to define our base and recursive cases. For the base case, if the set is empty, the only subset is the empty set itself. In the recursive case, we take a set S and remove one element, let's call it X. We first generate the power set of S minus X, then combine it with all subsets where X is included. This step-by-step approach allows us to build the full power set by breaking the problem down into smaller parts. Before creating the power set function, let's take our recursive logic and apply it to a slightly larger set S equal to 1, 2 and 3. We'll start by finding the power set of the smaller set 2 and 3. Remember, it does not matter which element you exclude first. You only need to exclude one element. Here we are excluding 1. The power set of 2 and 3 is the empty set, subset with element 2, subset with element 3, and the subset with elements 2 and 3. Next, we add 1 to each subset of the power set of 2 and 3. And finally, we combine the subsets from the power set of 2 and 3 with the subsets that include 1. So the full power set of 1, 2 and 3 is the one that you see at the bottom line, which is empty set in the individual elements 1, 2, 3, and the element subsets with 2 elements 1, 2, 1, 3, 2, 3, and finally the set itself 1, 2, 3. By repeating this process for any set, we can always find the complete power set using recursion. Now that we have seen the logic, let's look at the actual recursive function that generates the power set. We start with the base case. If the input set is empty, the only subset is the empty set itself, so we return an empty set. Next, for the recursive case, first we exclude the first element and recursively find the power set of the remaining elements. Then we include the first element by adding it to each subset in the power set of the smaller set. Finally, we combine the subsets that exclude the first element with those that include it, and that's our power set. Let's try this in PyCharm now. Here we have the power set function, which we just saw earlier. Let's run this function by passing different sets. Set with no element, set with one element, set with two elements, and the set with three elements. Let's run the program. When we pass an empty set, we get the base case, which is just the empty set. With element 1, we get the empty set and the set with element 1. With 1 and 2, we get these subsets, and with 1, 2, and 3, we get these subsets. As you can see, the function builds up the power set step by step, making it a powerful example of tree recursion in action. To wrap up, we have explored tree recursion through Fibonacci and power sets. While recursion provides an elegant solution, keep in mind that it often requires optimization. I hope this helps clarify how tree recursion works and when to use it. Thanks for watching.